So my name is Matthias Hille, and I will talk about SemperOS, a distributed capability system, which is joint work of Nils, Asmussen, Pramod, Bhatotia, and Hermann, Härtig. So we thought about how a distributed system would be built based on capabilities, and how exactly the rights management would be done in such a system. So typically, the system consists of nodes, and each node has a local capability system, which is managing the access rights locally, and then the resources of a node are exposed via some kind of interface, typically a POSIX interface or something like that. And out of these nodes, we built the distributed system itself. So to actually reuse the benefits of using a capability system, like building a system with the principle of least authority, we want to enforce the capabilities on a global scale. So we would like to put the distributed capability system in the distributed system, so the capability system in the distributed system itself. So, and the question now is, can we build such a capability system? Does it scale once we have it at that size, or is it a showstopper itself? And to get ready, I want to make sure we're all on the same page when I talk about the capability. So for me, a capability is a pointer to a resource with the associated access rights, and here the stickman is resembling a process which has a capability that points to a resource, and the capability itself is also recorded in a capability tree inside of the operating system. This tree is later on important to implement things like revocation. If the process now wants to share the access with another process, it can delegate the capability, which grants the second process access to the resource. So that's how you could, for example, establish shared memory. And this delegation can be done multiple times. If the sharing is now no longer desired, you would initiate a revoke operation, which causes the operating system to search the capabilities in the capability tree that need to be revoked, and then revokes the accesses from the processes. So this is one way of implementing revocation the way that we use. And we searched for capability systems and looked at several of them and tried to do a little bit of characterization in terms of their scope and how they enforce the access rights and how scalable they are or could be. And the first one is actually a class of capability systems like the L4 systems, with SEL4 and Fiasco as one of their two of their implementations. So they are implemented on cache coherent systems, meaning their scope is basically the cache coherence domain. And the enforcement is done via the memory management unit for all sorts of memory-related resources, or for the kernel for virtual resources like communication channels, something like that. And in terms of scalability, it probably scales as long as your coherence domain scales. Then there's M3, which some of you might already know due to the other talk earlier on M3X, which is a hardware-software co-design which does not rely on cache coherence and therefore scales to a machine as long as the components are connected via a network on chip or a network in the side of the machine. And the enforcement is done by a unit called data transfer unit, which the DTU, or for other resources, for virtual resources by the kernel as well. So, and M3 in its version, the base version, is using one kernel, which then becomes the scalability bottleneck if you use more and more cores. And then there's also Barkhausen as a capability system, which also does not rely on cache coherence, so it has the scope of a machine and is shown to be scalable up to 32 cores. So since we are in Dresden very familiar with M3 and it's the latest research development prototype here, we decided to use M3 as the basis of our system. So M3 runs one kernel, which is running on this dedicated core, and it's on a privileged core. And this core remotely configures the application cores that are shown in yellow here. It configures the DTU of the core, so the cores can only access resources they have appropriate access rights to. So this system call mechanism also works kind of different. The process running on the application core sends a message to the kernel and requests any kind of resource or service it wants. And similarly, an application would request, for example, a communication channel to be set up, and then the kernel configures the DTUs of the rightmost application cores appropriately so they can talk to each other. In SemperOS, we extended this to be a multi-kernel design. So we partitioned our system, which is shown here by the colored boxes. And each kernel is managing the application cores in its partition and also the capabilities of its partition. But the relations between the capabilities can cross partition borders. So we need somehow a mechanism to identify relations between those partitions, which actually are between different kernels. And that's what we call the distributed data lookups. Now here in this example we have kernels and kernel A and B, two partitions, and these kernels have processes, which are the stickmen over there. And these processes have capabilities, and we already know how to do this capability measurement in the local partition, but now we also have these cross-partition relations. And let's look into the capability itself. We have an ID, and then a capability has a parent and a list of children, typically. And we use this ID as sort of a fat pointer, so we use a particular part of this ID to identify to which partition a capability actually belongs. So now we have two separate, or at least two separate partitions with parallel operations going on, kernels working on the capability tree, on the global capability tree in parallel. So what could possibly go wrong? I will walk you through two examples. The first one is a problem that appears during revocations. So we have three partitions in this example, three processes, one per partition, and a capability that has been delegated from the first to the second and to the third partition. Now there are two revocation operations appearing. So these are two separate operations appearing at the same time. The first, the leftmost process revokes its own capability, and the second, the middle process, revokes the capability as well. So in a simple implementation, kernel A and kernel B would simultaneously clean up their capabilities and then send messages to the other kernels, following down the graph of the capabilities to remove the other caps. So now kernel B thinks that there's no capability anymore because it already deleted capability C, and it sent the request to kernel C, which is kind of busy at that time, and so the revocation is still waiting to be finished. But kernel A actually thinks the revocation is done. So in this point in time, we have a race where kernel A thinks the revocation is done and could give the resource to someone else, but actually the process in the third partition still has access to it. So, and a second problem we come across is when we look at the delegation. In this example, we use the same example basically, but we add a fourth process to the first partition, and we again have two parallel operations. The first is the revoke for the first process in partition A, and the second operation is a delegation in the partition of kernel B. So this delegation shall be done to the fourth process, and now the next step is that kernel A thinks, okay, I will clean up this capability here, and then send a request to kernel B to clean up its capability. And in the same time, kernel B sends a message that it pushes a capability, the delegation of C2, to kernel A. But it does not yet have a connection that connects C2 with the new capability. Instead, it cleans up C2, and kernel A, in the next step, creates the capability that it just received from kernel B. But this capability is basically an orphan, so there's no parent capability of that. And there's also no way to go back that way. So there's a capability that is a security risk at this point in time. When the revocation finishes, this capability is left over, and then the process there, the fourth process, has access to resource which it should not have. So we solved this by implementing it in a kind of a two-way handshake fashion. So I will just show here the delegation operation itself without the second operation in parallel. So if we do a delegation, we actually send a message to kernel that's quite the same. And now the kernel A just does a sort of a reservation for the capability. It does not yet insert the capability into the program, into the process. It just identifies it sets up an ID and then sends a ready message to kernel B that contains this ID. So kernel B can actually make a connection in the children list, the list of children of capability C2, sends an acknowledgement, and now the connection is set up. And this would have prevented the error we had in the scenario earlier. So we looked at all kinds of interferences that can appear with the capability operations we have in our system, and we also discussed the solutions in more detail in our paper. For example, the revocation problem we solved with a sort of a distributed mark and sweep algorithm, and then we combined all of this together in a protocol that's solving the distributed capability systems issues here. We evaluated our system in a Gem5 simulation where we used 640 out-of-order cores in the, yeah, exactly. And we had application traces recorded in Linux, and then we replayed them and their taming behavior in SemperOS, in which we implemented all the necessary system calls. The OS service we use is a file system, which is heavily used by the applications. And this is an in-memory file system, which uses the capability system to give an application access to a file. So we have a file and multiple extents, and if you open, read, or write to that file, you get a capability to a range of memory. And this range of memory is within this file. Now, if your read or write operation exceeds this range of memory, you will go to your servers again, and the servers will grant you access to another memory capability that gives you the next extent, basically. And if you close your file, all the capabilities you got for this file will be closed again, will be revoked again. So we selected a number of applications. Among them is tar and untar, who pack and unpack a number of files, find, which searches a directory, basically, and then SQLite as a small database engine, LevelDB as a key value store, where we insert and select and remove some values, and PostMark as a file system benchmark. On the left two columns, you see the number of capability operations that happen if you execute one of such application. And these numbers are kind of small because we had to strip them down to keep the simulation time in a reasonable time frame. So that's the reason why. And if we, on the right side, you see the number of capability operations and the operation rate if we execute 512 capability application instances in parallel. So there we achieve up to 348,000 capability operations per second for the PostMark benchmark. So we did a number of measurements, and I want to show you one here for those applications that shows the parallel efficiency, which is basically showing the performance overhead that one application instance experiences if it is run in parallel with a number of other instances of the same application. So 100% parallel efficiency shows the ideal scaling, basically. We reached a parallel efficiency of 72 to 78% in this configuration, where we use 11% of the system cores for the OS. And there we have different configurations that we looked at in the paper, where we use less or more cores for the kernel and less or more cores for the file system service. And we also discussed the trade-off between the system efficiency to use the cores for the application or for the operating system. You can find the details in the paper. We had another application implemented here, which is the Nginx web server, where we modified one of the cores to be a network interface, which floods the application cores, which are now Nginx processes, with requests. And yeah, they answer as fast as they can and stress the file system in this moment as well. Here you see some of the various configurations. So if we use just 8 kernels and 8 services, basically 8 cores for a kernel, we have 8 partitions in that system, and 8 services. We do scale not so far, but if we use 32 kernels and 32 services, we scale almost linearly. So to conclude, we built SemperOS which includes a scalable distributed capability system. We build up on global knowledge about our capabilities. We have an efficient identifier scheme, and we reach up to 78% of parallel efficiency when we use 11% of our cores for OS services. And it seems like, finally, capability systems do scale, and we will look further into this. So I'm happy to take questions.
Well, let me ask you a question. So I really appreciate the amount of evaluation, but I'm still a little bit confused about what is the main kind of insight. How do you scale?
Okay, so I think that scaling to 512 applications with a reasonable amount of overhead is good so far. I'm not sure how it would look like if we scale to 2,000 cores, but what
probably you misunderstood me. I would trying to understand what is the technical or what kind of set of mechanisms and abstractions you use to provide this scalability.
Okay, so we try to keep the traffic, for example, for revocation low. We do not spread so many copies. We do not spread so many cache copies of capabilities in comparison to other capability systems. So we always know where an object is in the system, where a capability is in the system, so we know where to go. For example, if we have capabilities spread across the system, there's no broadcast or anything involved that would not scale easily to bigger numbers.
Thank you.
Hi, John Crizzle, University of Rochester. I apologize for my confusion, but with the workloads that you tested, I don't understand where the delegation and revocation operations are coming from.
Okay, so the workloads, they all make heavy use of the file system, and the file system delegates memory capabilities to you. So you have, each time you open a file, you get a memory capability to that file, and each time you close it again, it's revoked again.
Equivalent to a Unix file descriptor, correct? So,
if you see
when you say you get a capability of the file, it's kind of like in Unix, you get a file descriptor to the file, correct?
If you see the Unix file descriptor as a capability, it is, yes. And then you delegate it. And the difference to the file descriptor is then that you know who has a capability, and you can revoke all of them. So.
Okay, so you basically have delegation and revocation between the operating system and the application that wants to open the file and close the file and so forth and so on. The file system has all the memory capabilities to all the files in the system. And the file system then delegates parts of this memory access rights to the application, and it uses the operating system to do so. Okay, so these capabilities are actually capabilities for memory locations. They're not capabilities to operating system objects.
The ones that we stress most in those applications are to memory objects, yeah, to memory ranges.
All right, maybe we should chat offline.
Oh, sure.
Thank you.
Marius Koga, CPFL. Thank you very much for the talk. So effectively, you have a distributed system, and there are some operations that have to be in order and some other operations that can be performed in parallel. So can you draw an analogy with literature related to distributed systems and state machine replication? So can you say that you could run something like Paxos or Raft and have different instances running in parallel?
We can definitely run Paxos and Raft in such a system, but I'm not sure what you're hitting
I mean,
at.
for the capability management. Because you try to solve the problems so you're going after specific problems, while effectively you need to order operations, and there are some operations that need to be ordered and some others that can be in parallel. So could you do something like running Paxos instances for the operations that you do need to order?
So if I get you correctly, then you mean that there could be multiple orders of the operations, and you want to choose which order the system agrees on. But I don't see the situation where we would need an election, for example, of a leader to decide on the order. So I don't really see what Paxos would give us here.
Okay, thank you.
Thank you.